This time we are going to prove some important properties of inner product spaces, or inner products in short, but basically it's inner products. So here we're going to show the linearity to be true, symmetry, and scalar multiplication property. Okay, with these components for your x. By the way, I forgot to edit this one here. Please pardon me. I'll be changing this. This should be capital letters because we're dealing with vectors. Okay, is equal to x and y plus x and then z. Here, same thing, x, y, according to symmetry, y and x. They are all capital letters except for c here. This is actually x and then c, y is equal to this. Because we're going to use the vectors themselves. Either way, understandably, it's just like that. Okay, now we have here these properties, and we're going to show the validity of these properties for us to be to use this later on in some examples further. So for linearity, we need to show that by the way, before we start, there are also versions of these properties that works not only for real numbers but even in complex. But since we are just on R2 and it's Cartesian plane, meaning we have the real numbers, so these are the equivalent properties for inner products in R2. This means here I might be using some of the space below. You have x, y plus z. We're going to show that from here this will return to this item here. Okay, so please pardon me if I'll be using, or I'll be jumping this portion and moving to the next side because the space might not be enough. Take note that for x here, basically its components are x sub 1 and x sub 2, but the sum has treated this as one vector. Let me write here, take note, so that we will be guided. Let's take note. Y plus z is equal to y sub 1, y sub 2, plus z sub 1, z sub 2, okay? So that its first component should be y sub 1 plus z sub 1, and then y sub 2 plus z sub 2. Because if we talk about inner products, we actually know that if we are going to have, say for example, let me write it here, you have a and b, and a, you will have here a sub 1, b sub 1, their first components, plus a sub 2, b sub 2, right? So this would be the first component, so we multiply the first component of that. In short, this would be here, your first component of your x sub 1 times the first component of the sum, like that, okay? And then plus, you will have here your second component, y sub 2 plus z sub 2. Again, please bear with me, I will be using some of the spaces below. So from this, you can use the distributive property x sub 1, y sub 1, plus x sub 1, z sub 1, plus x sub 2, y sub 2, plus x sub 2, z sub 2, right? Distributing them like that. Take that our goal is to show the inner products of x and y alone and x plus z, meaning let's pair those terms with x sub y and x sub z. By commutative property, x sub 1, y sub 1, plus x sub 2, y sub 2, then plus x sub 1, z sub 1, plus x sub 2, z sub 2. So we have this and that. And this is actually just equal to, okay, equal to the inner product of vectors x and y on the other side, multiplying the first components of x and z. So you have x here and z. We have shown that from here, we reach this portion, this item here. In short, linearity works for inner products. That's one of the properties we're trying to prove here. Let's proceed to the second one, which is symmetry. Symmetry tells us here, pardon with that, let me use this portion here so that I could use the scalar portion to that. Symmetry tells us that if we are going to take the inner product of x and y, it's just equal to the inner product of y and x, so the same components. Okay, so from here, so you'll have x and y. Take note the product of that is x sub 1, y sub 1 using the first components of the vectors plus the product of their second components. Take note, we would like this to happen, so we simply use the commutative property per term, y sub 1, x sub 1, plus, sorry, that's y sub 2, x sub 2. Since we already interchanged them, and the first for term is y, this is equal to y and x here. So we have shown that symmetry is also true for inner product. So if you have situations later on and you'll be asking if the result is still the same, if you interchange which vector is written first, according to this property, they're just the same. Now, let's proceed to the scalar multiplication property. In the linearity, this tells us that if one component or one vector is a sum of both, simply break them, pair those or separate those components to be paired with the first vector, right? Here, we're also going to show that if we have C, or one of the vectors is a multiple of or scalar C, simply take that out, and that's equal to the product of that C to the result here. Let's show that to be true, but of course, let's start with Cy first. Cy is C times the component y sub 1, y sub 2. This means this is Cy sub 1, Cy sub 2, right? That would be the components for this vector here. So that if we have x and then Cy, take note that for inner product, multiplying the first components, the first component of x is x sub 1, the second is x sub 2. So you'll have here x sub 1 times the first component of your Cy is Cy sub 1 plus x sub 2 and then the second Cy sub 2. I would like to rearrange all of this starting with C here because these are now real numbers. We can simply use commutative property and you will have here x sub 1, y sub 1 plus the same C, x sub 2, y sub 2. Since we have common here, common factoring, you have C, x sub 1, y sub 1, or no longer needing parentheses, you will have here times x sub 1, y sub 1 plus x sub 2, y sub 2. And what is this? This is actually the inner product of the vectors x and y. That's actually C times the inner product of x and y. So we have shown it from here. If you have a multiple here, simply take that out. You can have this equivalent to that. Take note, these are properties, and for some situations later on, we can just simply try to use these properties, and that will be for the next videos. We have proven 3 properties of inner product here, and we will see that on the next video. Thank you very much for watching.